Just want to talk about the basics of inequalities today. We have a number of statements here. We have 3 and 2, and 3 is the bigger number, and so we use the sign, a greater than sign, the sign with the opening towards the biggest number, to represent that 3 is greater than 2. Alright? So that's a true statement. Next one, we have -7 and -5. And the least negative number is the bigger number, and so the opening of our symbol is opening, the mouth of the sign, if you want, is opening towards the -5, and we would say that -7 is less than -5, which is a true statement. Alright, next statement, we have 3, and 3 is equal to 3, but we have here a less than sign. Is 3 less than 3? Well, no, it's not, so that's false, because we know that 3 is equal to 3. This is the part that's true. Now I bring that up, that's an obviously not true, but I now bring that up because we're going to start seeing things like this. 3, a less than sign, and then a line under that. And this symbol means less than or equal to. And in this case, since 3 is equal to 3, this is a true statement. So now what we want to do is we want to graph the solution to inequalities in which we have an x appearing on the number line. So let's just look at the statement I have. I have x, which represents the numbers I want to find. The numbers I want to find are greater than 4. And the part over here says that the numbers I'm looking for are elements of the set of, that's what this Greek letter epsilon means. They're elements of the set of real numbers. And remember, real numbers are basically all numbers we know, fractions, decimals. So what this statement is saying again is we want to highlight the numbers which are greater than 4. So on my number line, I'm going to identify 4, which is right there. And numbers that are greater than 4 would be to the right. So I'm going to color in all these numbers. I'm going to highlight them with a solid line, put an arrow to show that all the numbers in the shaded region make this true. So for example, 6, if I were to pop 6 into that statement, I would have a true statement. 6 is greater than 4. Okay? Now let's just talk about 4 for a minute. If I were to substitute 4 into that statement, this would not be a true statement. Okay? And so to show that I want to represent every single number from 4 to the right, except for 4 itself, I put an open circle. Okay, so that means that 4 does not satisfy this inequality, but 4.0001, let's say, it's greater than 4. This number does satisfy it. So the open circle means 4 is not part of my solution, but every number right up to 4 except 4 is. Numbers coming from the right, that is. Alright, here's another situation. We have -3 is less than or equal to, because of the line under the sign, x. So the numbers we're trying to find, which are x, the numbers that we want to be able to substitute in here, you can see the x is the bigger side of the two statements. Even though it's a less than sign, the numbers I'm going to fill in here will be bigger than or equal to -3. And again, we want numbers that are members of the family of real numbers, so all numbers. So if we put -3 on our number line, -4 would be here, etc., -2 would be here. We want numbers, again, to the right, so we're going to shade in, color in all of these points. So for example, -2 in there would be a true statement. But if I put -3 into x, would I have a true statement? Well, yes, I would, because -3 is equal to -3. And so to show that I do want to include -3 in this question, I put a solid dot on -3. Anything that's colored in or solid means it's part of the solution. You can put -3 into that statement and it's true. You can put 0 into that statement and it's true. But if you put anything in the uncolored region into that statement, it's not true. So what we're highlighting with the number line are the numbers that make the statement true. Next, I have what appears to be almost the same question. -3 is less than or equal to x, but this time the numbers I'm selecting have to be members of the set of integers. And you'll remember that integers are positive and negative whole numbers. -3, -2, -1, 0, 1, 2, 3. Those kind of numbers. Okay, -4. No decimals, no fractions. Those are not integers. Those are real numbers. So if I put my numbers back on the number line, -3, -2, let's just highlight what these are in each direction, just labeling them. Alright, so I want numbers that when substituted into here make this a true statement. Well, -3 still makes this a true statement, so I'm going to highlight -3 with a dot. What other integers make this true? Well, -2 does, and all of the integers going towards the right. But you'll notice I'm not coloring in the whole line because we're not talking about numbers in between. So a number in here, for example, -2.5, this is not a valid statement because this number is not an integer. And so that's how I would represent the set of numbers. Let's just change the question one more time. Same question, except now we want numbers that are natural. Natural numbers, remember, are numbers, the counting numbers, 1, 2, 3, 4, on and on and on. So -3 is shown in the question, and we want all the numbers that are natural numbers more than or equal to -3. -2, -1, 0, 1, 2, 3. I'm just labeling. I'm not yet highlighting. But now that I do want to highlight the numbers that are more than or equal to -3 that are natural, the first one would be 1, then 2, then 3, then 4, and numbers going on in that pattern. All right?